Okay, welcome students. We're going to do a lesson on ionic bonding. And we're going to start just by talking about bonding. We talk about what it means to be full, to be happy. Noble gases are generally happy. When they're not, then bonding is required. So an atom will attempt to bond to get a full outer shell. Now, the first question is, we'll do a recap on valence electrons. So you'll see that as we move across the periodic table, left to right, you'll see that the valence electron number increases. So you start with 1, 2, 3, 4, 5, 6, 7, 8. And so magnesium has a valence of 2. Silicon has a valence of 4. And if we look at something like sulfur, it has a valence of 6. It means that there are 6 electrons in the outer shell. How would we show that? Well, Bohr Rutherford's is one way, but they're very cumbersome. So we would more likely use Lewis dot diagrams, a much better way to show that. And we can see that if we look at the Lewis dot diagrams, the patterns for the periodic table, you'll see if you go down the second group, you'll see that they all look very similar, just with those 2 dots each time. So beryllium, magnesium, calcium. And because of those valence, they have very similar properties. So, how does an atom achieve a full outer valence shell? Well, this move to a stable octet. Sometimes that position of happiness is called a stable octet. So they have a full outer shell. It's achieved by the movement of electrons, and it's the movement of electrons that produces bonds. So in the diagram that's here, oxygen starts off with has 6 valence electrons, and hydrogen has 1 valence electron. And so the question is, how can hydrogen and oxygen get full outer shells? Well, oxygen is going to need 2 more to get up to its preferred full octet, and hydrogen only needs 1. Because remember, the first shell, you only need 2 electrons in the first shell. And that's why in water, it's not random. There's 2 hydrogens and 1 oxygen. So each one of the hydrogens contributes 1 electron, and the oxygen has a full outer shell. Now, it has to be said that what we've looked at is a covalent bonding example, but it's just the one that we're most familiar with. So there's 2 different types of bonding. One is covalent bonding, one is ionic bonding. Ionic bonding is always between a metal and a non-metal. So for example, a good example of ionic bonding is sodium chloride, between the metal being sodium and the non-metal being chlorine. The other point we need to say is ionic bonding. In ionic bonding, one atom loses an electron and one gains. There's a transfer. Okay, so that transfer also produces ions, which we've talked about. They have opposite charges. And as you know, opposites attract. That old saying in life, love, and chemistry, opposites attract. Ionic compounds also have no net charge. So what that means is the positive and the negative should balance out. And another key point about ionic bonds is ionic bonds, or substances with ionic bonds, conduct electricity. Okay, so here's an example of sodium chloride, which is an ionic structure which has ionic bonding. The sodium loses, the metals normally lose an electron, and so the electron moves from the sodium to the chlorine. And what you get created is a sodium ion, Na+, and a chloride ion, Cl-. You'll notice it's called chloride, not chlorine. If we look at that in terms of Lewis dot diagram, what you would simply see is you have a sodium with 1 electron, and that moves over, and the chlorine is now going to get that extra electron. Now the chlorine has a full outer shell, but the chlorine also has an extra negative, so we have to put -1. The sodium has now got rid of an electron, so instead of having a electron count of 11 electrons, 11 protons, it now only has 10 electrons and 11 protons, so it has a +1. When showing an ionic bond through Lewis dot diagrams, you must show the brackets and the charge, and also when there's a positive and it's lost an electron, You don't have to show any electrons in there. It will have a full shell sitting underneath that, and that's why it's happy to give away the electron. Okay, so sodium and chloride ions, they will bond in a structure known as salt, and they're pretty tightly packed, and you'll have a situation like at the bottom. So the chloride negative ions and the Na plus. Okay, what ratio do atoms normally combine? Is it always one is to one? So one sodium, one chlorine, that worked, but the answer is no. So magnesium has 2 valence electrons. If we look at it on our periodic table, it has 2. It has 2 valence electrons. Now chlorine, it turns out, has 7. Okay, so chlorine, from your gizmo, you should have realized that chlorine will just need to take on 1 electron to get a stable octet, 8 electrons in its outer shell. Now, how does it do that? Well, if you have the magnesium, magnesium will always, to get back to become a noble gas, the quickest way, rather than taking on electrons, is to lose 2 electrons. So it will lose 2. If it loses 1, it becomes the same number as sodium. But if it loses 2, it has the same number of electrons as neon and has a full outer shell. So it goes from 12 electrons down to 10. And because of that, it becomes a 2 plus. It becomes a 2 plus. Okay, so that's what it's going to form. And the Cl is going to be a Cl minus. Now you have to match up the pluses and minuses. So the 2 electrons that are lost by magnesium atom are gained by chlorine atoms. In other words, magnesium is going to give away 2, so you're going to need 2 chlorines to take those electrons. And so what you end up with is you end up with magnesium, just 1 of them, and 2 chlorines. So it's MgCl2. Each chlorine will have a negative, and the Mg will be a 2 plus. So if we're to show this in terms of Lewis dot diagram, we're going to put the one with the biggest charge always goes in the center, 2 plus. So magnesium 2 plus, and we're going to show the chlorines out here. Now each one of these chlorines did have 7, and it's received 1 from magnesium. Okay, to become -1. You will also have the chlorine out here, and that will have 7 of its own, plus 1 donated from magnesium. So now we have magnesium is 2 plus, the chlorine is -1. When you have 2 -1s, it's overall -2. So +2 -2 means a neutral 0 charge. Those charges should add up to 0. Okay, so what about aluminium and chlorine? Well, if you look at the valence in aluminium and you look in your periodic table, it will tell you that aluminium likes to become Al3 plus. Chlorine, on the other hand, we've talked about, is a -1. So how do you balance those charges? Well, you're going to need 3 chlorines to balance up the charge to get an overall charge. Of 0. Okay, overall is equal to 0. So you +3 and -3, when you add those together, it's 0. And so when you're figuring out the overall formula, it's AlCl3. So it's an AlCl3, and there's 3 chlorines, 1 aluminium. Okay, so how do we show it with a Lewis dot diagram? Well, you guys should be able to do that. We've already shown you how to do it. You will have 3 chlorines, and remember those square brackets. Okay, so just some tips on this. Determine the charge that each ion would have. Balance the charges so they add to 0. And then you can also use crisscross method of stuff. I'm going to show you crisscross very quickly. When you have the elements, you determine the charge on them, +3, and the Cl -1. Crisscross is kind of like a shortcut way to write the formula. So you're literally just bringing down the number. So you're bringing down the 3 over here, and you're bringing down the 1 here. and that would be your formula. I don't necessarily always like students using crisscross because it's just kind of a cheap shortcut, and that would leave you with AlCl3. It's called the crisscross method, but basically the charges should balance. Okay, what about sodium bonding with sulfur? Can you draw the Lewis dot diagram for that bonding? Well, first of all, you would write out your charges. You would need to write your formula. So you're going to write the charges. Then you're going to determine the formula. Determine the formula. And then write Lewis. Okay, I'll leave that for you guys to practice. I've done a couple of them. So it may not be a 1:1 bond. Right, so the final thing is naming ionic compounds. Ionic compounds are formed between a metal and a non-metal. The metal is always written first and non-metal second. And to name a compound, follow the steps. Write down the symbol for the metal. Write down the name of the non-metal. But you have to change the ending to "ide". So an example would be sodium chloride, or know that sodium could bond with fluorine just as easily because one forms a positive one and the fluorine will form a negative one. So when you're writing out this ionic compound, you put the metal name first, and the non-metal you change the "ine" to "ide". So you change the end of it to "ide". Just some ones to look out for: oxygen changes to oxide, nitrogen to nitride, and sulfur changes to sulfide. Okay, so these are all very simple names. So the names are very, very simple unless there's a couple of exceptions. One is a group known as polyatomic ions. And these are ions that float around with multiple atoms involved. There's 3 examples up on the top right. The hydroxide ion is OH minus. The sulfate ion is SO4 2 minus. And the nitrate ion is NO3 minus. So if we look at the 3 examples provided, we have hydroxide. We said this was sulfate. And this one is nitrate. Now you have to memorize these, unfortunately, and on the right there's common polyatomic ions, and I will also provide you with a list from class, but it's beneficial to start remembering the top 6 or 7 of those. Okay, in order to name them, when a sodium ion bonds with a hydroxide, what's the name of the compound formed? Well, the compound formed in that case is pretty straightforward, actually. You would have NaOH, which is equal to sodium. We always put in the metal name, and then just the name of the polyatomic, sodium hydroxide. It is NaOH. Be careful to make sure the charge is balanced. So Na would have a charge of +1, and OH has a -1. So we don't need to put any subscripts down in the bottom here. The subscripts will just remain as 1:1. So remember, the ratio of how they combine is very, very important. So the final part here, so there's exceptions. That's exception number 1 in ionic bonds. You may have a situation where there's polyatomic ions. Second thing, you may use transition metals, or there might be transition metals in there. Now, we talked about skipping transition metals before. Transition metals are a little bit odd because they have many valences. They're multivalent. I'll give you an example: iron oxide. Iron oxide can have a valence of 2 or a valence of 3. Now they look very, very similar. These names, iron 2 oxide, iron 3 oxide, look very similar to each other, but they're in fact very different compounds. The one on the left is iron 2 oxide, it's black. The one on the right is rust. It's a rust color. Okay, so iron 3 oxide is rust. Now if you're given a formula, how do you figure out what the name of iron oxide is? So it does end in oxide, and it does have the iron at the very beginning. So in that respect, it's very similar to the basic ionic names. The only difference is you must show its charge. The reason is because its charge can vary, so we have to explicitly say what its charge is. So let's look at an example, FeO. When we look at FeO, we must work back and realize that the charges must balance. So the Fe charge, which we don't know, must balance with an oxygen charge, which we know to be -2. The oxygen will become -2, and you just have one of each. And we know that these charges must add up to 0. So one -2, therefore the iron must be a +2. So you have a +2 and a -2. And so this +2 charge finds its, works its way into the name. So it's called iron 2 oxide. And you use Roman numerals to show that the charge is +2. If we look at the one on the right, we now look at Fe2O3, and we write this down. There's actually 2 Fe's and 3 oxygens. Okay, oxygen will always have a charge of -2. And if we go through the same thing, we'll see that this is equal to -6. And so we need a +6 with our iron charges. So it means that the charge on the iron must be +3. And that would give us a +6, and overall we'd have a 0. Okay, so these charges must cancel. And that leaves us with an Fe of +3. And that must feed its way into the name. So after the iron, you must say the charge. So it's iron 3 oxide for that reason. So there's some of the examples in terms of naming. We talked about what ionic bonds are, and we talked about naming. And just some things to remember. Electrons are transferred in ionic bonds. To figure out the ratio, you must determine the charge. You can use crisscross. And when naming ionic compounds, it's pretty straightforward, apart from when there's multivalent elements involved. These are the elements in the middle of the table, and polyatomic ions involved. Okay, so the next lesson to tune in for is covalent bonding, and hope you enjoyed the lesson.